So in this video I want to look a little bit more at limits. And I want to focus on the idea that a limit is not the value of a function, it's the value the function's approaching. So I have a graph here of f of x is equal to x squared minus 3x plus 2 over x minus 2. And it looks like the graph of a line, right? But it has a little hole when x is equal to 2. And that's because if we factor the numerator of the function, we'll get x minus 2 times x minus 1 over x minus 2. And we can cancel those factors and get x minus 1. So this function is going to be identical to x minus 1, which is just a line at every point except when x is 2, because when x is 2 our denominator is undefined. So if I ask you, well, what is f of 2? Well, you try to plug 2 into the function, you're going to find it's undefined because you can't divide by 0. But I can say, what is the limit as x approaches 2 of x squared minus 3x plus 2 over x minus 2? Then I'm saying as I'm coming up this curve in the x direction, or both ways, so I'm coming from above 2 and below 2 and converging to the point when x is equal to 2, what is my y value converging to? Well, I can't just plug 2 in because it's undefined there, but I can do some algebra to simplify it and then plug it in. Because if I factor my numerator, we found it simplifies. So it'll be the limit as x approaches 2 of x minus 2 times x minus 1 over x minus 2. We factor those, or cancel the factors. It will be the limit as x approaches 2 of x minus 1. And we found if we plug 2 into that, we get 2 minus 1, 1. So that's the limit. That's what the y value is approaching. And if you look at the graph here, when x is equal to 2, y is equal to 1, it's converging on that point where there's the hole. So the function's not really defined there, but the limit exists. And that's the whole idea behind limits and what makes them so powerful, because the function doesn't have to exist or be defined there. It just must be converging to the same point in both directions as x converges there. So let's look at another example I have here, and this is a pretty common thing that we'll see moving forward in calculus. So if I say, what is the limit as delta x approaches 0 of the square root of x plus delta x minus the square root of x over delta x? Well, if I just try to plug delta x in, I'm going to be dividing by 0. It'll be undefined again. And I can't factor it like I did the previous one. But another thing we can do, a little trick with our algebra, is to multiply by the conjugate of the numerator. So if I do that, it'll be multiplied by x plus delta x, the square root of, plus the square root of x, divided by the same. So we're not changing any values, we're essentially multiplying by 1. But when we multiply out the numerator, we'll get the limit as delta x approaches 0 of x plus delta x minus x, because when we multiply that out, that times that will clear the square root. We get that times that and that times that, but those opposite signs are going to cancel out, and then we multiply those two, we get our x term. So that simplifies our numerator and gets rid of the square roots, and in the denominator we're left with delta x times that whole quantity we're multiplying. So does that help us much? Let's look at what we can do with this. We see we have an x and we have a negative x. So we can cancel those two out with one another. And then we have just delta x in the numerator. So we'll have delta x over delta x times the square root of x plus delta x plus the square root of x. And then we can cancel those delta x's out. So then it will become the limit as delta x approaches 0 of 1 over the square root of x plus delta x plus the square root of x. And what does that do for us? Well, we can just plug delta x equals 0 in for that, and we'll get 1 over the square root of x plus 0 plus the square root of x, which simplifies to 1 over 2 square roots of x. And that will be our limit. So for any value of x you want to plug into that, our limit's 1 over 2 square roots of x. And we can apply this idea with conjugates to a lot of different functions. You'll see it a lot as we deal with square roots and different things, that this is a little algebra trick we can do to find the limit. Because once again, the function doesn't exist, or it's not defined at the point we're looking at the limit. But as we approach that point, it's approaching a given value, and we can find that doing a little algebra. So in this video I want to look at the idea of limits, which is kind of foundational to what we're going to do with calculus. And probably more important with limits is not as much understanding what a limit is as understanding what it's not, because it's a common confusion. And really a limit is saying what is the function approaching, or what is the dependent variable approaching as the independent variable approaches a given value. And to make that a little more concrete, let's see an example here. If we have f of x equals x squared plus 3, or 2. If I said, what is f of 2? You would just plug 2 in, and you'd say that's 2 squared plus 2, which would be 4 plus 2, 6. Well, if I ask you about limits, we'll say, what is the limit as x approaches 2 of x squared plus 2? And again here we would plug it in. We'll say, okay, that's 6. However, what we're in our first example, when I said what is f of 2, we're talking about what is the value of the function when x is 2. When we're talking about limits, we're talking about what is it approaching. So it's as you're getting infinitely close to 2 with our x value, what is y getting close to? And if we think about a graph, x squared plus 2 will be a parabola shifted up 2. It'll look something like that. As x approaches 2, we're saying as we come along this curve, as x approaches 2, we'll say is a point around there, what is y approaching? Well, it's 6. And we can apply this quite easily whenever the function's defined there. We just plug the value in, and that will be its limit. But something that makes limits more significant is we can do it when a function is not necessarily defined at a given point. So if, say, I ask you for the limit as x approached 1 of x minus 1 divided by x squared minus 1. Well, if you try to plug 1 in for x, the function's undefined because you'll be dividing by 0. But we can factor the denominator. That'll be the same limit. We'll have x minus 1 over x plus 1 times x minus 1. Then you'll see we cancel factors. That will be the limit as x approaches 1 of 1 over x plus 1. And then we can plug 1 in. That will be 1 over 1 plus 1, 1 half. And what we're saying in this is that on this curve, x minus 1 over x squared minus 1, as x is approaching 1, the y value is approaching 1 half. And the secret to this is that the function is not defined at 1. It's undefined. There's a hole in the graph there. But as you're getting infinitely close to it, your y value is getting infinitely close to 1 half. And we can apply this in a lot of different ways as we move forward in calculus.